Welcome to the knowledge sharing of APM32 series MCU controller area network. The knowledge sharing contains 5 aspects. The first is the bus knowledge and module knowledge of CAN, then the use of APM32 CAN and the IAP demo of CAN, and the final is the summary and review of this sharing. CAN is the abbreviation of Controller Area Network, and is the Serial Communication Protocol of ISO International Standardization. The CAN communication is similar to surfing the Internet. We judge various kinds of information and titles on the Internet, then open and read them. Since there is no concept of address, the CAN nodes can freely join and exit the CAN network. Due to the simple wiring, fast transmission speed, and high security, CAN is mainly used for communication between various components of automobiles. In the in-vehicle network using CAN as the communication protocol, we can see that the components of the same speed are connected by a single CAN bus to form a communication network, while the communication networks of different speeds are connected through a gateway, so that they can transmit data. In communication network, the components are transmitted in the broadcasting form, and the ID represents the type of broadcasting. Other components will judge whether the data is the information they need according to the ID before receiving. The CAN bus can be divided into high-speed CAN and low-speed CAN in terms of speed. The high-speed CAN uses a closed-loop transmission network and requires a resistor to be connected between two lines. The low-speed CAN uses an open-loop transmission network, and requires a resistor to be connected in series on each node. Currently, the structure of high-speed CAN is mostly used. The function of the resistor is to accelerate discharging, make the bus quickly enter a recessive state, improve the anti-jamming capability of the bus, eliminate the impedance discontinuity and mismatching of the bus, and improve signal quality. We see that the CAN is composed of 2 lines, and these 2 lines form a differential bus, so that the CAN has good anti-jamming capability. The level of the bus is formed based on the judgment of these 2 lines, which are a dominant level and a recessive level. The dominant level is logic 0, while the recessive level is logic 1. Data transmission means that CPU transmits data to the transceiver through the CAN controller, and the transceiver converts the data into differential signals and transmits them to the CAN network. We can know that the communication circuit of CAN is very simple, and in order to complete some complex communication, we need to define various aspects of the data packets it transmits. First, let me introduce a type of CAN data packet and the types of frames. There are 4 types in total, namely data frame, remote frame, error frame, and overload frame. The remote frame, also known as remote control frame, is the most important data frame. The composition of the data frame is shown in the following figure. It consists of 7 parts. The first is the frame start of a dominant level. Next is the arbitration segment, which contains the ID information of the data frame. Next is the control segment, which controls the number of data on the data frame. The data segment is the data of the data frame, with a maximum of 8 bytes. The CRC segment is used as the receiving end to conduct CRC on the received data. The acknowledge segment is mainly used for acknowledging. The transmitting terminal sends the recessive level, while the receiving terminal sends the dominant level. At the end of frame, it has 7 consecutive recessive levels, so that the bus returns to an idle state. The data frame also has some individual bits, for example, RTR is a remote request bit, and when it is dominant, logic 1 is a data frame, and when it is recessive, logic 1 is a remote frame. The IDE only has 1 extended ID flag bit. When it is dominant, it is a standard ID, and when it is recessive, it is an extended ID. For example, the above segment is a standard ID, and it is a standard data frame. However, in the following segment, its ID is recessive, and it is an extended data frame. R0, R1 and SSR are reserved bits. At the beginning, the standard ID of CAN is 11 bits. With the increase of demands, its ID is increased by 18 bits, and becomes a 29-bit extended identifier. The above is the introduction of data frame. Next is the remote frame. The difference between the remote frame and the data frame is that the former has no data segment and its RTR is a recessive level. In the above segment, its ID is a dominant level, so it is a standard remote frame. In the segment below, its ID is a recessive level, so it is an extended remote frame. The remote frame is mainly used to notify the corresponding ID nodes to send data, which is mainly implemented through software. Next is the error frame, which means that if the CAN detects an error from the line when receiving and sending messages, it will transmit an error frame to the bus. The error frame is mainly composed of error flags and error delimiters. The error frame is divided into active error and passive error. The active error flag has 6 dominant levels, while the passive error flag has 6 recessive levels. The last is overload frame. It is mainly used for the receiving units to notify other unit that it has not been ready to receive. The overload frame consists of overload flags and overload delimiters. After introduction of the types of frames on a CAN bus, the bus arbitration of CAN will be introduced. The CAN adopts multi-master control. Then what is multi-master control? It means that when the bus is idle, each unit connected to the bus can send messages. So it can be considered as having multiple masters. When 2 or more units simultaneously send data, the data sent needs to be arbitrated bit by bit in order to avoid conflicts. Arbitration is conducted mainly through the CAN readback mechanism. What is the CAN readback mechanism? That is to say, when the CAN is sending message, it will compare the message with the level connected on the bus. If they are consistent, CAN will continue to send the message, otherwise, it will exit the sending state and return to the receiving state. Take the Unit 1 and Unit 2 as an example. When the bus is idle, pull the bus to a busy state. When the 5th bit is sent, Unit 1 sends a recessive level, namely logic 1, while Unit 2 sends a dominant level, namely logic 0. Due to the characteristics of the line, the bus presents a dominant level. At this time, Unit 1 reads back the level of the bus and finds that it is inconsistent with the level it sends. Therefore, Unit 1 will return to a receiving state and Unit 2 will continue to send. So we can know the functions of some protection bits. For example, the SRR bit is used to ensure that the priority of one standard frame is higher than that of the extended frame. Then we can know that the priority from high to low is the standard data frame, standard remote frame, extended data frame, and extended remote frame. After the introduction of CAN frames, the bit timing of CAN will be introduced below. Each bit of CAN is composed of 4 segments, namely synchronization segment, propagation time segment, phase buffer segment 1, and phase buffer segment 2. Each segment consists of several time units, and the synchronization segment is a fixed time unit. The CAN transmits data mainly through 2 lines, and we can know that it does not have corresponding clock line. Therefore, the CAN needs to synchronize the clock according to the set timing in order to read data normally. There are 2 methods for synchronization of CAN. The first is hard synchronization. Hard synchronization refers to the synchronization of the start frame conducted when it is detected that the bus changes from idle to busy state, that is, at the time of the first falling edge. This falling edge will be taken as the synchronization segment, and samples will be taken according to the specified bit timing. Due to possible delay errors on the transmission line, there may be delay after hard synchronization. Therefore, synchronization needs to be conducted again, which is the second synchronization method of CAN, namely resynchronization. Resynchronization is to synchronize each falling edge after hard synchronization to determine whether the falling edge is exactly on the synchronization segment. If not, increase or decrease the time segment 1 and time segment 2 by 1 unit based on the difference in time units between the synchronization segment and the falling edge, so that the synchronization segment can exactly fall on the falling edge in the subsequent bit timing. For example, in the first case, its falling edge is before the synchronization segment, and the clock is ahead. Therefore, the time segment 2 will be reduced by 1 time unit, so that the subsequent synchronization segment can just fall on the clock edge. In the second case, it has a falling edge, which is after the synchronization segment. The clock lags, so one clock unit within the time segment will be increased by one time unit, and the subsequent synchronization segment can just fall on the clock edge. At the same time, in order to avoid clock deviation and receiving data errors when resynchronization has not been conducted for a long time, the CAN protocol stipulates that every time 5 same levels are sent, an opposite level will be inserted to create a falling edge and make resynchronization occur. After the introduction of the CAN bus knowledge, the CAN module will be introduced below. When CAN is used, first we need to have a certain understanding of its module. The CAN module mainly consists of several parts. The first is a basic register of CAN. It is mainly used to configure its baud rate, operation mode, and interrupt configuration. Next is a sending mailbox and 2 receiving queues, and the last is a filter. The baud rate of CAN is 1/bit timing, and we know that a bit is composed of several segments, and each segment contains several time units. This time unit is the CAN clock divided by its frequency division value. Therefore, the calculation formula of the baud rate is the CAN clock/frequency division value of CAN/ the number of time units per bit. For example, in F103, the CAN clock is 36 M, and when its frequency division value is 6, the BS1 is 2 and the BS2 is 3, which means it has 6 time units per bit, and the baud rate is 1 M. This is the operation mode of CAN. The CAN has 4 operation modes in total. The first is the silent mode. In silent mode, the CAN does not send data to the bus, but it can read messages on the bus, so this mode is mainly used for listening. Next is the loopback mode. In this mode, the CAN does not read some data on the bus, so it is unaffected by the bus, but it sends information to the bus. The loopback mode is mainly used for self-test on the CAN to test whether the CAN can operate normally. The silent loopback mode has the characteristics of the above 2 modes. The last is the normal operation mode. In this mode, it can send data to and receive data from the CAN bus. The next is the filter. The filter is a tool used by nodes to filter messages, and it judges whether the message is needed according to the ID before receiving. The filter has 2 modes, namely list mode and mask mode. The list mode filters the entire ID, while the mask mode filters the values at the specified position of ID. For example, in the list mode, we set the filter to 123, there are 3 messages on the bus, namely 122, 123, and 134, the CAN will only read the message 123, namely the message with an ID of 123. When the filter is set to the mask mode, the value of the mask is 12x, which means that only the first 2 bits are compared, and the CAN with the same data will recycle the data of 122 and 123. In our CAN module, 2 32-bit registers form one set. In the list mode, 2 registers can store one identifier. In the mask mode, one register is used to store the identifier, and the other register is used to store the filter codes, to filter the values for comparison. So it has several modes, and in the 32-bit list mode, it can store 2 identifiers, and can identify 2 types of ID. In 32-bit mask mode, it can only store one identifier and one filter code. In 16-bit list mode, it can store 4 identifiers, and the 16-bit mask mode can store 2 identifiers and 2 filter codes. For the messages on CAN bus, the selection of its filters also has priority. First, judge whether the 32-bit filter has priority over the 16-bit filter. The filter of the list mode has priority over the filter mode, and the filter with a small number has priority over the filter with a large number. Next is the transmitting mailbox, which mainly configures the information we need to send to the bus, such as ID, extension identifier, frame format, whether it is a data frame or a remote frame, as well as data length and byte data. The priority of the mailboxes is selected by software, and determined by the ID or the transmission order. The mailbox has several states, and normally it is in an empty state. When our software sends a request, it will be registered. At this time, if the current mailbox has the highest priority, it will become predetermined. At this stage, according to the predetermined state, it can be used to judge whether the bus is idle, and if it is idle, it will send. Of course, multiple nodes may send at the same time, so arbitration is needed now. If the arbitration is successful, it means the sending is successful and it will become idle. If the arbitration fails, it can only return to the receiving state, and the mailbox will become predetermined. If there is a mailbox with a higher priority registered at this time, the predetermined mailbox will return to the registered status. The last is the receiving mailbox, which mainly consists of 2 queues with a depth of 3. We can configure the specific mailbox that receives the message segment on the filter. Because its depth is only 3, it is probable that new data will be read in, but it has no location to store. Therefore, there are 2 solutions. One is to discard the new data, and the other is to overwrite the existing data with the new data. Some basic knowledge of CAN is introduced above. Now the use of CAN on APM32 will be introduced. First, let's learn the current chips of our company with CAN module. The first is the F072, F091, F103, F105, F107, F407, E103, and S103 series. The chips of some models only have 1 CAN, others have 2 CAN, and the CAN of some models is a master-slave CAN. What is master-slave CAN? The master-slave CAN refers to CAN 1 and CAN 2, which share a set of filter group, such as 2 dual independent CAN. Normally one set of CAN has 14 groups of filters, and 2 CAN, 14 groups of filters are CAN 1, another 14 groups of filters are CAN 2, and their filters are independent. The CAN 1 of the master-slave CAN has 28 filters, and the CAN 2 can determine the specific filters of the CAN 1 it uses only by configuring a starting memory on CAN 1. Like this example. Therefore, when the CAN 2 of the master-slave CAN is configured, we need to turn on the clock of CAN 1 to configure the CAN 1, and CAN 2 can use the filters on CAN 1. Next is the code filter. In fact, the CAN code is simple, and is mainly divided into several parts. The first is a CAN 1 pin. For example, here a PD1 and PD0 are used as the CAN 1 pin. After the pin is configured, configure the operation mode of the CAN. Here, the CAN is set to a normal operation mode, and the baud rate of the CAN is configured to 1M, which is because it is also a CAN of F103, and its CAN is 36M, and according to calculation, its baud rate is 1 MHz. We need to note that this synchronization segment 1 actually includes the propagation time segment and the buffer segment, so at least 2 time units are required. When you configure it as a time unit, the CAN cannot send data normally. After the baud rate operation mode of CAN is configured, configure the operation of some filters on the CAN. Here the CAN filter group 1 is configured to a 16-bit list mode to filter the standard frames with an ID of 0x0321 and the remote frames with an ID of 0x0321. Its receiving mailbox is configured as a FIFO 0, and when configuring its identification mask, we need to pay attention to the alignment position of its registers. For example, its 11-bit ID corresponds to the 15 bits of the register, so this 0x0321 needs to be shifted left by 5 bits. If the FIFO 0 identifies and filters the remote frames, this bit should be set to 1, combined with a remote and shifted left by 3 bits. Finally, if you want to send, it is configuration of a transmitting mailbox. In fact, the transmitting mailbox is the information we send to the bus. When we send a standard data frame to the bus, its ID is 0x321 and has a data byte of 0x55. That is its configuration. However, when the CAN 2 pins of the F103 series and 1203 series need to be remapped, we need to note that if they are remapped from other pins in the remapping group, the remapping of the CAN 2 group needs to be put after the remapping of other pins of the remapping group, otherwise, the CAN 2 will be unable to communicate normally. This precaution is also included in the remapping function. The last is an IAP demo of CAN. This is IAP upgrade using a CAN. Firstly, the upper computer sends the firmware to an intermediate machine through a serial port, and the target machine will make an upgrade request to the intermediate machine. If there is upgrade firmware in the intermediate machine, it will send the firmware to the target machine. The specific IAP upgrade flow chart is shown in the figure. The intermediate machine waits for the upper computer to send the firmware, and after it receives an upgrade request but there is no firmware, it will continue to wait. If there is firmware, it will send the firmware. The target machine will send the upgrade requests constantly. This is a recorded video. On the left is the intermediate machine, and on the right is the target machine. First, the target machine sends an upgrade request to the intermediate machine constantly. When the intermediate machine receives the firmware, the light will light up, and then the firmware will be sent to the target machine. After the target machine receives the firmware, it will jump to upgrade. The upgrade request mainly uses a remote frame. The target machine sends a remote frame to the intermediate machine, and the intermediate frame identifies the remote frame and can determine its ID information to confirm that it is an upgrade request. Therefore, the remote frame requests sending data mainly through software. The last is the summary and review. We mainly discuss four aspects, namely the bus knowledge of CAN, which includes the topology of CAN bus and the type of frames. Next is the arbitration and bit timing of the CAN bus. Then we discuss the module knowledge of CAN, mainly including baud rate calculation, operation mode, filters, and transmitting and receiving mailboxes. The last is the use of CAN, and I mainly introduce which chips have concurrently and the precautions for remapping of CAN when F103 is used. The last is IAP design demo of CAN, and the use of CAN remote frames. That's all for today. Thank you.